Well, welcome to our final discussion here in Chapter 2. We've been studying functions and some of the properties and characteristics of them. In the last lesson we looked at how to graph them and shifts and different things with symmetry. Today we're going to talk about different operations that can be done with functions, adding, subtracting, multiplying, dividing, and the idea of composite functions, composing two functions, decomposing two functions, and then looking at domains and so forth. So we'll start out here with this box. Now you'll probably think as you look at this that this may be fairly intuitive, and that'd be alright. If we add two functions together, f plus g, both in terms of x, well, that's just the same as f of x plus g of x, and that's really the same thing with sum and difference, product and quotient. And so we're asked here in part A to find the sum, difference, product, and quotient. We look at f plus g of x. Well, we know that's simply f of x plus g of x, which is the square root of 5 minus 2x plus the square root of x plus 3. And so that's my sum. The difference, f minus g of x, is f of x minus g of x, square root of 5 minus 2x minus the square root of x plus 3. The product here, fg of x, well, that's simply f of x times g of x. So we're working at the square root of 5 minus 2x times the square root of x plus 3, and we know then that that would be the square root of 5 minus 2x times x plus 3, both of those underneath the radical. And then finally we look at the quotient of f and g, and so this is f of x divided by g of x. Now we're going to have to be a little careful that g is not the zero polynomial, and it's not here. This is the square root of 5 minus 2x over the square root of x plus 3. And now in part B, they want us to determine the domain of the sum, difference, and the product. So what we're going to do, we have to make sure, of course, that 5 minus 2x is greater than or equal to 0. Which means that negative 2x is greater than or equal to negative 5, and negative 2, we divide both sides. Of course, remember, we need to flip that inequality, so x is less than 5 halves. We also have to make sure that x plus 3 is greater than or equal to 0, so x has to be greater than or equal to negative 3. And so, as we look at both of these, x has to be less than 5 halves, and it has to be greater than negative 3. Now, perhaps you're having trouble seeing this result. Let's go to the colors here just momentarily. Let me grab my red. X less than 5 halves, less than or equal to 5 halves. Well, here we go there. That's in red. And then let's look at x greater than or equal to negative 3. That's in blue. And so what we've got here is this region from negative 3 to 5 halves. That is our domain. We've got to make sure both of those are satisfied. Now, for the domain of the quotient, alright, we're going to have the same domain with one exception. If we look here at the quotient, we know that the denominator can't be 0. Alright, and so when we get ready to identify the domain of the quotient, we have to take out negative 3, because if x were negative 3, then I would have division by 0. And of course we can't have that. So there we go, that's our domain for the sum, difference, product, and quotient. And if you'd work problem 8 for class and then 3, 5, 7 for class discussion, we'll be good to go. Alright. Now let's take a look at, as I've typed here in the notes, some terminology that will be used often throughout the rest of your mathematical lifetime. A function is a polynomial function if f of x is a polynomial. That is, and pay attention to this line right here. You're going to see in math books and us math teachers write something like this quite a bit. And all this is saying, guys, you know, you're comfortable with polynomials. F of x equals, say, 7x cubed plus 2x minus 3. G of x equals negative 4x squared plus, oh, I don't know, 9x minus 11. Guys, just different polynomials like that, where in this case, you know, we've got a sub 2, x2 plus a sub 1, x to the 1 plus a sub naught. And we think of a sub 2 as being the coefficient in front of the coefficient of x squared. A sub 1 is the coefficient of x. A sub naught, that's our constant. Remember, coefficient's a big fancy word that just means number in front of. So that's what we're looking at here when we think about these polynomials, and you're going to see this a lot. This form, f of x is a sub n x to the n plus a sub n minus 1 x to the n minus 1, all the way down to a sub 1 x, notice this is to the first power, plus a sub naught. Now we'll notice here, you know, they tell us in this paragraph a sub naught, a sub 1, all the way up to a sub n are real numbers, and the exponents are non-negative integers. Alright, so you know, it can be 0. That's what we've got here. X to the 0 is 1. A polynomial function may be regarded as the sum of functions whose values are of this form, cx to the k, where c is a real number and k is a non-negative integer. Note that the quadratic functions considered in the previous section are polynomial functions, as we've just talked about. An algebraic function, guys, you've always wondered, right, what an algebraic function is a function that can be expressed in terms of finite sums, differences, products, quotients, or roots of polynomial functions. And so they give us an algebraic function here. Of course, we just added some polynomials and radical functions a little bit ago. Functions that are not algebraic are called transcendental. The exponential and logarithmic functions considered in Chapter 4 are examples of transcendental functions. More on that as we come. In the remainder of this section here, and I know you guys are capable of reading, but I want to point a few things out as we go here. In the remainder of this section, we're going to discuss how two functions, f and g, may be used to obtain the composite f of g and g of f. Now, guys, I know our text says read f circle g and g circle f. Let's make note right now, f circle g, I'm going to say, is read f of g and not f circle g. And I think you'll find most math instructors, most mathematicians are going to say f of g, g of f, and not f circle g. You say, well, that's great. You can call it what you want to, and you can, you know, say it's pronounced however you want to pronounce it, but what's that really mean? Boy, am I glad you asked. Let's take a look here at the definition. The composition f of g of two functions is defined the following way. And we basically take g and plug it into f anywhere we go. You might think of it like this. This is one place in the world where instead of going left to right, we kind of go right back to left. Let me show you what I mean here. Let's take a look at example 2, part A. F of g here. F of g of x. Well, let's see. I'm going to take g and I'm going to put it into f everywhere I see an x. Alright, so this is 3 times 4x squared, because that, after all, is what my g is, minus 1. And so this is simply 12x squared minus 1. So we continue now to look at the composition of functions here in part B. Let's take a look at g composed with f. Now this time we are going to put f into our function g here, g of f of x, and we'll notice that f is 3x minus 1. We're going to put that right in here into g. So this is 4 times 3x minus 1 squared. Alright, well this is 4 times, we know what 3x minus 1 squared is. That's 9x squared minus 6x plus 1, or 36x squared minus 24x plus 4. We look at part C, And we need to find f of g of negative 2. Now, folks, I'll tell you the way I'm going to handle this. I'm going to find g of negative 2 first. G of negative 2, that's going to be 4 times negative 2 squared, which is 4 times 4, or 16. And so now we've got f of g of negative 2, which is f of 16. And f of 16 looks like 3 times 16 minus 1. 48 minus 1 is 47. And then finally, looking at part D here, we have what? We have g of f of 3. Well, I'm going to do the same thing again. G of f of 3. Let's take a look here. Let's first find f of 3. Alright, this is 3 times 3 minus 1. 9 minus 1 is 8. And so now what we have is g of 8 equals 4 times 8 squared. And so let's see. You know what? Yeah. So g of 8, 4 times 8 squared, of course 8 squared is 64. And we're going to multiply that by 4 to get 256. Okay, 256 there. And so now for class discussion, if you'd kindly work problem 18, we'll talk about that. Of course, always feel free to bring your questions in, and then also we'll take a look here at 15, 16, and 17 for homework. Now we're going to do something a little bit differently here. We're going to find, first of all, the compositions of these, and then once we do that, we're going to find the domain. Now, when you get ready to do this, if you read in your book, you've got to kind of look at three things, really: the domain of f, the domain of g, and then their intersection. So let's take a look here and see what we've got for part A. For part A, we're looking at f composed with g, so this is f of g of x. Well, let's see, we're going to put g into f, so this becomes the square root of, instead of x, I'm going to write what g is, and g is x squared plus 2x minus 15. Alright, now that's my composition. When it comes to finding the domain, I know that x squared plus 2x minus 15 has to be greater than or equal to 0. Well, this is x plus 5 times x minus 3. And boy, it's a good thing we studied those polynomial inequalities back in the last unit. Let's take a look here and see what we've got. We know that we look at our number line at negative 5, we have a 0. At 3, we have a 0. And so we've divided our number line up into 3 regions. And we'll pick test points here. Let's see. Let's go x plus 5, x minus 3. And so let's go with x equal negative 6. If I put negative 6 in here, that's a negative. That's a negative. Negative times a negative is a positive. And then let me go with maybe 0. That's always a nice one. 0 plus 5 is positive. 0 minus 3, that's a negative. And so we're negative there. And then let's go with x equal 4. So 4 plus 5 is a positive. 4 minus 3 is also a positive. And so we know that if we're going to keep that radicand positive, if we're going to keep that radicand positive, we have to make sure that for the domain, x needs to be either from negative infinity to and including negative 5, or we need to pick up at 3 and go to positive infinity for the domain. Alrighty, so let's look now at part B. And so for part B, we're going to go the other way. We've got g composed with f. So I'm going to put f now in everywhere I see x and g here. So this is going to be the square root of x minus 15 squared plus 2 times the square root of x minus 15. And of course, the only concern here is we've got to make sure that x minus 15 is greater than or equal to 0. Not a big deal at all. Nice linear inequality. X is greater than or equal to 15. Interval notation here, 15 to infinity, and there we go. There we go. Alright, so if you have questions on that, please feel free to bring those to class. Now, we're going to look at 32. And 32 is going to take a little work, as you might imagine, not just in finding the composition, but in determining the domain. And we've got to watch out, because we can't have division by 0 at any part in the process. Now, let's identify a couple things here. Domain of f is going to be all reals except 2. And the domain of g is going to be all reals except 0. Alright, so we need to keep that in mind. Now let's look at f composed with g. So what I'm going to do, this is f of g of x. So I'm going to put g into f everywhere I see an x. Alright, so this is 3 over x divided by 3 over x minus 2. Well, we know this is 3 over x divided by 3 minus 2x over x, which turns out to be, and this is supposed to be minus 2x here, we know this turns out to be 3 over 3 minus 2x. But the one thing that we've got to watch out for on this, as we look here in this work, okay, as I look here in this work, and here's what I'm considering, right here, 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 and here. I cannot let any of those spots become a 0. And so because of that, my domain here is going to be all reals except for 0 and 3 halves. All reals except for 0 and 3 halves. Alright, now if we look at g composed with f, we know this is g of f of x. Well, let's see. I'm going to put f of x in here in for g. So this is going to be 3 over x divided by x minus 2, which we know this is 3 times x minus 2 over x. So the things we have to watch out for, I can't have a 0 here, nor can I have a 0 here, and so my domain here is going to be all reals except for 0 and 2. By the way, is everybody comfortable how I got this result here? If not, let me just go through this briefly. This is 3 over 1 divided by x over x minus 2, and so this is 3 over 1 times x minus 2 over x, which is 3 times x minus 2 all over x. So a little thinking bubble maybe to help you out if your rational expression operations are a little rusty. We'll try to help you out there. So here's our function compositions, one domain and then the second domain. And so for class discussion, we're going to work problems 24 and 30. And then for homework, if you'd kindly work that list of problems there, we'll be good to go. So as you begin to think about what I might include on a quiz or on a test for this particular section, the big thing here, folks, is adding, subtracting, multiplying, dividing, and composing functions. F plus g, f minus g, f times g, f divided by g, f composed with g, and g composed with f, and find their domains. That's going to be the big concept, big objective that we're going to want to think about on section 2.2. As always, please, please, please write down any questions that you might have. Bring those to class. We'll be happy to talk about them.